Hello everyone, welcome to my presentation titled MPC-Based Multi-Inverter Power Control in Low-Inertia Power Systems. The objective of this work is to extend the capabilities of our previously designed controller, called the Inverter Power Controller, from a single inverter to multiple inverters running the controller in the network, thus enabling them to participate effectively and efficiently in providing frequency control response. This extended capability also allows for the inverters to operate either under a centralized or a distributed control structure, depending on measurement availability. For more information on our previous work, do check out the reference below. The general idea of the IPC controller is to capitalize on the fact that the power flow between buses in the power network is proportional to the angle difference between the buses. Therefore, if we use the angle of the inverter as a control variable in an MPC-based optimization problem, then we can determine the additional amount of power each inverter should produce in the event of a disturbance to the grid. The objective of the optimization problem is to determine the amount of additional power that minimizes the frequency deviation and rate of change of frequency in a network. If there are multiple inverters running the controller, then an additional power sharing constraint is added to the optimization problem to ensure that the power output is weighted based on the capacity of the participating inverters. Under the centralized control algorithm, a central server, which has access to all measurements in the network, runs the algorithm to determine the optimal power set point for the participating inverters in the network and sends these set points to the inverters. While under the distributed algorithm, each of the participating inverters receives partial information depending on availability or proximity and uses an estimation algorithm to estimate the missing information before individually running the distributed MIPC algorithm to determine their individual set points. We tested this algorithm on the New England 39-bus 10-generator system using the centralized MIPC algorithm. The figures show the frequency of some select generators and the output power of the inverters as the number of inverters providing frequency control response in the system increases. When there is only one inverter in the system, that is inverter 5 at bus 34, the central server runs the regular IPC algorithm and the inverter output power is as shown in the leftmost plot. In the middle left plot, when there are two inverters, that is inverter 3 and 5, the centralized MIPC is used to determine the appropriate participation of the individual inverters. The participation and power sharing ability depends on the capacity of the inverters and can be accounted for using the weights in the optimization problem as discussed in the previous page. The same process occurs when there are 3 and 4 inverters participating as shown in the middle right and rightmost plot. It can be observed that an increase in the number of inverters does not adversely affect the overall performance of the controller, and the inverters are able to work in tandem to share the responsibility of quickly minimizing frequency oscillations in the network. We test the performance of the distributed MIPC algorithm on the same system and compare its performance to that of the centralized algorithm. Under this controller configuration, two inverters are participating in providing frequency control response. Inverter 3 at bus 32 receives information from the generators with the red circles, while inverter 5 at bus 34 receives information from the generators with the green circles. It can be observed that the distributed algorithm initially results in more frequency deviation and uses more inverter power compared to the centralized algorithm. But as the estimator becomes able to accurately estimate the unavailable states and disturbances to the system, each inverter running the algorithm is able to determine what its optimal power output should be. In conclusion, from the results, we see that the algorithm is effective in enabling multiple inverters provide frequency control support both in a centralized and distributed control structure. For future works, we would look into the optimal placement of these inverters in the network to best provide frequency control services. Thank you.